Hello, welcome back. I am Victoria and this is Corey, and we are the Professor's Stew Boys, and today we're going to be continuing on with our thermochemistry unit, and we're going to be talking about the heat transfer between two objects today.
So, handshaking isn't that common these days, but at some point in your life you probably did shake someone's hand, and you might have experienced where the person you were shaking hands with had very cold hands or maybe very hot hands. And it's really kind of interesting if you probably never really thought about this, like what's going on? So let's say the person had a really cold hand. Well, what you're feeling is you're feeling cold. And what that actually is that's heat leaving your hand and going to their hand. And just think about that for a second. The feeling of cold is heat leaving your body. And that's kind of interesting. Now, if you're feeling someone's really warm hand, what's happening is heat is flowing from their hand to your hand. So like we said before, heat flow high to low. So that feeling of cold is of particular interest to me because it's
kind of neat.
It's actually heat leaving your body. So we're using this word heat a lot in this thermochemistry unit, and we actually assigned a unit to it, the lowercase q. So we could say if the warm hand, there's heat's flowing from warm to cold, so that would have a negative q value, right? So the value would be negative because the temperature when these two hands, that's something I should have said, if these two hands stay in contact for a long enough time, they will no longer feel hot or cold because they'll come to the same temperature, and that we call that thermal equilibrium. So the amount of heat that's lost by the warm hand is equal to the amount of heat gained by the cold hand. Now, this has to be in a closed system. When we're shaking hands, there's air around the hands that would be taking some of the heat as well. But if we had a closed system, the heat lost by the warm object would be equal to the heat gained by the cold object. Now, you remember we solved for Q using the formula mc delta T. So we could substitute mc delta T's in for these Q's, and they would have equal values, but the signs would be different because of the delta T.
So we can kind of think about this as the law of conservation of energy, right? So the heat gained equals the heat lost. Now the negatives and the positives are really more talking about which direction the energy is flowing, not so much a value of negative value versus positive value, or something that's not there or of negative. It's really just the flow. So if the flow is going from the warm hand, the temperature is going down, and the heat, the amount of heat or energy that hand has, is decreasing. So that's a negative change. When the heat is entering an object, then the energy is increasing, and that's a positive change. But if you add the two together, the magnitude, so what's lost equals what's gained. If you add them together, it's zero. There's a net zero change in the entire system, or the whole world, universe, hasn't changed the amount of energy. So that's why we can add them together and it will equal zero.
I like to put numbers to things. It helps make sense. So let's say the heat lost was 10 degrees, or let's just not even put a unit on it. Heat lost is 10. So minus 10, heat gained 10, plus 10. Minus 10 plus 10 equals 0. Heat lost plus the heat gained equals 0.
Yeah. So more so the energy, the joules, when you add those changes together versus the temperature. So here's an example of if we have a hot object. Again, we just have it as a cube. Maybe it's a piece of metal.
Upper left.
Yeah. So if this is our hot object here, and it's in contact with our cold object, and we will have heat flow from high to low, and we can represent this with an mc delta T. So Q lost equals Q gained equals, if we add those together, it equals 0. We can expand that out to say mc delta T of what's losing heat plus the mc delta T of what's gaining heat equals 0. Now, since delta T is final minus initial, if you have something that's increasing in temperature, the final will be a larger number. So again, if we just use 10 and 5, we will have 10 minus 5 gives us a positive number. There's our positive Q. But if we have the opposite, the other object will be the opposite. So we have one that's positive and one that's negative, one that's gaining energy and one that's losing energy.
One thing that's interesting is when you have two objects of different temperature come into contact, they're going to come to thermal equilibrium. So the T final for both of these will be the same number.
Yeah, that's a very good point. This will be the same. Thermal equilibrium. All right, so here's an actual type of question that you might see. So we have a hot piece of metal, and we have an initial temperature. We call that Ti. And we're going to drop that into the water. The water also has a Ti, and they will maintain in contact with each other until thermal equilibrium is reached. So the heat will flow from the metal into the water until they're the same temperature. So this is the T final for both.
Now notice that the metal lost a lot of temperature. Notice I didn't say heat.
Right.
Because the heat lost was the same as the heat gained. But look at the temperature difference. The metal went from 99.8 to 23.1, and the water only went up a little bit. Now, there is a lot more water there by mass, but this ties back to that specific heat capacity. If you remember in our previous video, that water has a high specific heat capacity.
Which means it takes more energy to change its temperature. All right, so we break down our data. We have a mass for our metal. We're solving for our specific heat. So maybe it's an unknown metal. We don't know what it is, and specific heat is something that's intrinsic to the specific material. So this could be one piece of information that helps us identify an unknown metal. And we have our change in temperature of our metal. Again, it's much larger than the magnitude of the change in temperature of our water. But notice how our T final minus T initial gives us that negative number on the one side, and we have the positive on the other. That's how our negative plus our positive equals 0. So we usually are provided with with 7 out of 8 of these variables, and we can put them right into our formula and solve.
And the specific heat capacities are usually provided for you. But the water one we use so often, I think you'll end up memorizing that, the 4.184, but you'll have a resource or a chart to do these. So we simply punched in the numbers here, and I just wanted to kind of explain the second line down there. What we've done is we multiplied the 225 by the 4.184 times the 2.1 on the right, and our units canceled, the grams canceled, the degrees C canceled, and we were just left with joules. On the left-hand side, we multiplied the 55 by the negative 76.7 degrees C, so that number, the minus 42.18.5, now has units of grams degrees C, and then just times the specific heat of the metal, C metal. So what we started doing is we started moving stuff to the right next to get C metal by itself. So I took that plus 1976.94 and I subtracted it, and then I had to do the same thing on the other side. So it canceled on the left, and I have a negative on the right, and then the final step is to divide by the negative, and the negative divided by the negative will give me a positive value.
Here's a practice problem for you. And it might make you cry because you're solving for one of the temperatures, but it doesn't have to make you cry, because you can solve for, and we recommend this, solve for delta T first. So you have gold, and you're putting it into water. So you have masses, you have temperatures, you have your resulting mixture, so that's your T final for both. Okay, your T final will always be the same for both, but you have to solve for the initial temperature of one. And we recommend solve for delta T, and then you'll have delta T equals T final, which is given, minus T initial, and then it's just an easy way to find your T initial. So give that a try and pause the video.
Another thing is they didn't provide the specific heat capacity for water, and that is 4.184 joules per gram C.
Yep. You want to use that. All right, so there's your answer. Hopefully you were able to obtain that. If not, go back through and try to practice what we showed you. And we will see you on the next one.
All right. Thanks for watching.
Bye-bye.